When we picture the growth of artificial intelligence, we usually imagine acres of new data centers, drawing massive power to support ever-expanding systems. To see why that infrastructure is ballooning, look at a modern frontier model. A typical large language model today might contain 400 billion parameters, operating at an original 16-bit, or BF16 precision. At 16 bits, each parameter takes 2 bytes. Multiply that out, and you need 800 gigabytes of video RAM to load the weights. In production, you must string together at least 5 $10,000 GPUs just to operate the model. For a business, those hardware requirements create immediate AI technical debt. The baseline costs are high, and the inference latency, the time it takes for a model to think, effectively destroys the speed and throughput users expect. When every new instance requires a cluster of 5 GPUs, scaling becomes a linear expense that outpaces user growth. To make AI economically viable, we have to move beyond adding hardware and start shrinking the models themselves. That shrinking process relies on a technique called quantization. Quantization is the science of reducing the numerical precision of a model's weights, so they take up less physical space on a chip. Instead of storing each parameter as a highly detailed 16-bit number taking up 2 bytes, engineers compress them into 8-bit or even 4-bit integers, dropping the storage cost to just half a byte per parameter. This chart illustrates the resulting memory overhead. By shifting from a standard BF16 model to a 4-bit quantized format, you achieve a 75% reduction in the model's digital footprint. You might expect a model that loses 3/4 of its mass to become significantly less capable. Yet a properly quantized model can retain over 99% of its original accuracy on reasoning benchmarks. Compression removes the mathematical redundancies without erasing the intelligence. The model operates on a fraction of the memory, meaning a workload that previously demanded 3 GPUs can now run rapidly on exactly 1. Treecapital AI engineered the Anven architecture around this specific efficiency. Their lightweight, 3 billion parameter model, Model 1, is built to maintain high fidelity even under extreme compression. This flowchart outlines Anven's 2 distinct latency reduction pathways, Method A during training and Method B post-training. Focusing on Method A, quantization-aware training paired with LoRa adapters emulates the impacts of quantization while the model trains. The system locks the model's core backbone into a light 4-bit format. Meanwhile, it uses LoRa modules, specialized adapter layers, to maintain the nuanced reasoning required for specific enterprise tasks. For custom-trained models, organizations use Method B, the spin-quant pathway, a post-training solution. As the heavy model passes through the spin-quant prism, rotation matrices suppress data outliers, producing a cleaner, 4-bit model without a new training cycle. Because spin-quant operates entirely post-training, developers can heavily compress their own proprietary models locally. They never have to expose their private training datasets to an external provider just to gain efficiency. By lowering the compute requirements, quantization moves intelligence out of centralized server farms and directly into the palm of your hand. Anven's footprint is small enough to run natively on the edge. Using the ExecuTorch runtime, these models can operate directly on mobile phones or embedded IoT devices without a network connection. This is the foundation of sovereign AI. Instead of sending requests to a cloud API, organizations can run their models completely offline, isolated within air-gapped virtual private clouds. For regulated sectors like healthcare or finance, localized inference provides a guarantee of data privacy. Sensitive records are processed on-device, where the organization has total control. Because the entire model fits on-premise, your enterprise data never has to cross a public firewall to utilize generative intelligence. We often assume that better AI requires endlessly scaling up parameter counts in the cloud. The mathematics of quantization point in the opposite direction. Looking at this waterfall chart of cost reduction drivers, you can see the impact of these efficiencies. Moving to localized 4-bit quantized models sharply reduces the total cost of ownership for an AI project. Offloading inference to the edge removes the recurring per-token fees of cloud APIs and significantly lowers the compute-to-revenue ratio of the entire stack. The future of scalable business AI is smaller, smarter, and sovereign. delivering hyper-efficient intelligence exactly where an organization's data lives.